Hello everyone, my name is Abida Ishaq and I'm going to present a project that requires us to produce 100 kg mole of butadiene alongside with my crewmate in Group 3. I shall start with the literature review. We managed to find a good resource from various journals that provide us with all the information that we need including the butadiene background and its properties. There are few processes for production of butadiene. First is the byproduct of ethylene, second is the production of butadiene from propylene, and the third is oxidative dehydrogenation of 1-butene using bismuth molybdate as catalyst. For the most typical reactor types that we use are the tubular reactor, fluidized bed reactor, and packed bed reactor.
Hello everyone, I am Hazim Shahmin, and as for my part, I'm going to explain the synthesis route and also the kinetic reaction. So for this project, we are assigned to propose with two possible routes for the best outcome of production of butadiene. So we have come up with the oxidative dehydrogenation as our first route and also the catalytic dehydrogenation for the second route. And these are the details that has been summarized into one table so that it is easy for us to make the comparison. Thus, we chose oxidative dehydrogenation as our synthesis route. Butadiene is effectively produced by an oxidative dehydrogenation reaction over heterogeneous metal oxide catalysts such as bismuth molybdate. And as for the reaction kinetics, based on the general equation, we can notate them into A, B, C, and D. For that, we can obtain the A plus half B equal to C plus D. And from the elementary reaction, we can get the rate law, which is negative RA equal to K, CA, CB. And according to the rate law, we can conclude that this is the second order reaction. Meanwhile, we can also calculate the value of K based on the parameters provided in the table 3. Following the formula of K is equal to AC to the power of negative EA over RT, we can obtain the K after we do the unit conversion.
For the reactor system, we choose to use packed bed reactor because it is good for oxidative dehydrogenation reaction and best for continuous testing of heterogeneous catalysts.
My name is Muhammad Ismail bin Muhammad Jan. So next I am going to explain about stoichiometric table. So as we can see here, here is our main reaction. Our reactant is 1 butene and oxygen, while our product is butadiene and the byproduct is water. So each component has their own symbol, and the next column is the initial. The other column is change, and then the final and their concentration. Next, I am going to explain about multiple reaction. So here is our main reaction, and here is the relative rates of reaction. So the relative rate of reaction is Ra over -1 equal to Rp over -1 equal to Rc over 1 and Rd equals to 1. So our rate of reaction for A is R1A equal to negative KACACB, while for B, our reaction rate is R2B equal to negative KACACB. For C is R1C equal to KACACB. And lastly for D is R2D equal to KACACB.
Next, I am Nur Adrina Alia and I'm going to present the calculation part. So with the operating condition of the PBR, which is T naught equals to 673.15 Kelvin, P naught is 2 atm, the conversion is 95%, the density of butadiene is 615 kg per meter cube, and the K obtained is 14.6124 mole per dm cube second. So we can calculate FA naught and V naught because it is given the product flow rate. So in case 1, due to the gas phase of the reaction, the V is equals to V naught 1 plus epsilon x. Therefore, we can substitute in the equation of Ca. Calculating epsilon, we obtain the value of 0. Then, after substituting the value of epsilon equals to 0 into the equation, we obtain Ca equals to Ca naught 1 minus x. Since the concentration for A and B are the same, therefore we can assume that theta B is equals to 1. Therefore, the equation for Cb is equal to Ca. The design equation for PBR is Fa naught equals to dx over dw equals to negative Ra, and the rate law is negative Ra equals to KCACB. And by combining both equations, we can calculate the weight of catalyst. For case 2, which is non-isobaric, since the reaction occurs in the gas phase, therefore there will be pressure drop. So we will change the equation for V, which is V naught 1 plus epsilon x P naught over P. And by substituting the new equation into the equation of the weight, we can obtain the new weight of catalyst.
My name is Nazrul Naim bin Fadli and I will explain the MATLAB part. So we have our calculation here and we insert the title calculation of butadiene case 1 and this is our assumption. We insert the value of the assumption and then we insert the formula of W which is Fa naught over Ka Cn naught squared times by the integration. So finally, at the bottom, we insert the command printf to display the value. For the next part, which is case 2 is non-isobaric, first we insert the printf for the title and then we insert the new W formula which is we add P1 over P0 to the formula and finally we at the bottom we insert printf to print out the answer. So basically after we run the program, so this is the answer that we get for the calculation.
Next, I'm going to continue the MATLAB calculation for the selectivity of butadiene and yield of all products. So in order to calculate the selectivity and the yield, we have to have the value of all the rate law for all species, which is Ra, Rb, Rc, and Rd.
In a nutshell, the process is oxygen dehydrogenation of 1-butene. The reactor used is PBr. The value of K is calculated by using Arrhenius equation, and we obtain the value of catalyst weight for both cases and the selectivity and yield value for the reaction. This is the list of references that we use to refer throughout our project. Thank you.